All right, hi everyone. Welcome to the next seminar. We're going to have a very exciting talk today from Niayesh Afshordi from University of Waterloo. He is a professor there and is working on astrophysics and cosmology and gravity and lots of exciting things that all of the audience are going to be very interested in. So thanks very much for taking out the time to give us this seminar. And I guess without further ado, I'll just pass it over to you. So thanks a lot, and take it away.
Thank you very much. Thank you very much for the invitation. I was hearing a beeping sound, but I think it's gone, so I think that's not a problem. Very good. Thank you very much for the invitation. I wish I could be there in person in superposition in various rooms across Australia, but here I am, and I'm going to tell you a story of despair and hope. Hopefully, we'll see which one of them is gonna win. So this is the outline of what I'm going to tell you about. I'm going to start with a very dramatic setup with the crisis in physics. And then I'm going to tell you about three different things that may help solve the crisis, or at least make us more comfortable living through the crisis. So depending on your point of view. Let's see. So, and please don't hesitate to interrupt me. I know it's the Zoom setup, it might be a bit strange, but again, I'm very happy to take questions throughout. And I mean, this talk is designed to be provocative. So don't take anything they say for granted. Probably they're all wrong, but still don't hesitate to point it out to me. Okay, so I'm going to start with the crisis in physics. So probably most of you have seen this in one way or another, but if there's a younger student among you, I just want to point out or remind you that we have chasms amongst our best theories and best observations. Quantum mechanics and relativity are pillars of modern physics, but if you combine them together, that leads to, and at face value, leads to infinities for essentially all observables. So that's not very good. We have singularities at the hearts of Big Bang and black holes that are very distinguished, ubiquitous phenomena we have in the universe. We have information that's apparently lost when black holes evaporate. We have dark energy, which is 60 orders of magnitude lighter than predicted by quantum mechanics and a standard model of particle physics. And there is this lingering question that is a standard model, which is the most fundamental theory of nature on subatomic scales, is it actually technically natural in a sense that I'm not going to define for you, but for those who know, this is an outstanding problem which has had many proposals for solve it, but hasn't really been solved. So there is a bizarre state that the fundamental and theoretical physics happen to be living in. And that could be a call for arms or a reason to despair or some combination of the two, depending on which state of your career you are in. We have something that may be a little bit more nuanced, but I call the crisis of falsifiability, that we have proposals for solving all of these puzzles, but none of those proposals appear to be testable, or at least either they've been tested and turn out to be wrong, or they cannot be tested for some reason. The string theory, which is the most popular proposal to unite quantum mechanics and relativity, appears to have 10 to the 500 vacua and then lots of other things that basically unpredictable. So you cannot get concrete predictions out of a string theory. There is no signature of any of the hallmarks of a string theory, in particular supersymmetry, anti-de Sitter space, or extra dimensions, that they're all things that are apparently predicted out of a string theory or other approaches to these fundamental problems. There is no concrete testable prediction from any quantum gravity, in fact. So even though string theory is the most popular one, the less popular ones, like the quantum gravity, causal sets, or others that some of my friends and colleagues at Parameter Institute work on, They are not in a better shape either. When you go into focus on early universe, we have this leading theory known as cosmological inflation, which is, again, similar to string theory, is the most popular one. But funnily enough, even though it does say something about data, no matter what data we observe, there is some inflation model that can fit it. So there's really no way to test inflationary paradigm, because apparently at any time in the past 20 years, the data have changed, come and gone, and there's always been some inflationary theory that was very successful in explaining it. And putting all of this together, the fact that we cannot really test any of these fundamental proposals, at least so far, you may wonder whether theoretical physics, as most physicists practice it these days, is turning into religious dogma. Now, this is something you may hear in crackpot emails that you receive every other day. But I mean, I think it is a genuine question that, in fact, you may assume some genuine practicing theoretical physicists may start to ask or have started to ask. So here I'm giving you the example of a typical theoretical physicist who are sitting in the middle and are dealing with this crisis. Sorry. On the one hand, they are trying to explain nature in a testable way, and we are having trouble. So we seem to have hit a wall of some sort. The progress has become slow. And we have lots of models, but very few ways to actually test them or confront them with data. And there is a lot of data, but still progress has been hard. On the other side, we have society, which is growing more and more skeptical of scientists and scientific methods. And we are kind of basically stuck between a rock and a hard place. And as physicists, we have to decide how to deal with this, this conundrum, this pickle. And I would actually tend to speculate that solution to these two crises are interrelated. But I leave that as a thought for you to take home. Again, as to practicing physicists who have been ringing the alarms, so here is a well-known astronomer, Christopher Stubbs, who was a good friend of mine. He used to be the dean of science at Harvard until last summer. And this is the colloquium that he gave at Perimeter Institute about 13, 14 years ago. And he basically is arguing that dark energy actually is in a state of crisis, actually is a harbinger of crisis in physics. And it might be a sign of intellectual stagnation in our approach to fundamental physics. In fact, his predictions are very telling. 14 years ago, he said, if we just continue to measure W of -1, that's a cosmological constant, there's no deeper theoretical ideas, and Large Hadron Collider detects Higgs and nothing else, and these predictions have all come to pass, then things look bleak. It will be difficult to extend existing techniques to higher precision. So, in fact, I emailed Chris right after he retired from his deanhood last summer, and he said that basically he agrees with this statement, and I think we are in this era of intellectual stagnation. And you can read more into it: religious intolerance, economic deterioration, etc. Other physicists, well-respected and well-known, they have been ringing the alarm from a lack of supersymmetry. This is the first one that was, I mean, we've been looking for it for a long time and haven't found them, to critics of basically whether mathematical beauty has misled physics, to confirmation biases that seem to confirm our preferred theories, but only to turn out that the data was in fact misinterpreted, to approaches to string theory. So my friend, many of these, actually all of these are my friends, and they all have kind of pointed out to different symptoms of crisis and expression in the state of theoretical physics. Most recently, this is actually from an interview with one of the forefathers of string theory who kind of suggests that the string theory itself is also in a crisis. So now, for those of you who are maybe younger and looking for upsides to all of this, or actually just generally more optimistic and young at heart, this is a quote from my favorite Canadian singer, being in Canada. That's what I'm obliged to do. Is to say that there's a crack in everything, and that's how the light gets in. Our job as physicists or scientists to find these cracks and then look through them to see the light. So the rest of this talk hopefully will be more optimistic, but also will become more speculative. And you can take it at different levels of grains of salt, again, depending on your knowledge and how open-minded you are. So I'm going to point out these cracks. So in particular, I'm going to point to something kind of strange and something that most theoretical physicists know about, but they rarely put them together. And I call it the conundrum of cosmic causality. So one of the deepest, kind of most sacred notions in theoretical physics, in particular in theory of relativity, is that nothing can go faster than the speed of light. And that's been the basis of special relativity and quantum field theory, which have been both incredibly successful, and general relativity for that matter. Nonetheless, there are, if we put all of this together and put them together with observations, we hit this obvious conundrum. One of them is on the left-hand side. We see black holes that are now well imaged and understood across spectra, both theoretically and observationally, and even gravitational waves. But then we know that if you add quantum mechanics to them, as Hawking famously shown, they're going to evaporate in vacuum. And somehow the information within them has to disappear or get out of their horizons, which violates the principle of causality, that nothing can go faster than the speed of light. So that's one problem. And similarly, on the other side, when you think about the Big Bang, and the universe turns out to be so homogeneous and isotropic, with very regular structure on larger scales, you appear to again violate the causality, because basically a causal point points across the CMB sky that have no causal connection in standard Big Bang appear to know about each other and reach thermal equilibrium, with very correlated structure across it. So they both, so these are both well-known problems, and both have been studied extensively in the past 50 years, 40, 50 years. In fact, we are celebrating 50th anniversary of Hawking information paradox, and then we are organizing a workshop in Stony Brook in the fall, basically to bring experts together and discuss basically what happened to these paradox over the past 50 years. But they're rarely put together. So they each have their own solutions. One is inflation, the other also severe stuff that you may or may not have heard about. But they both actually point to the same thing, that causality, when you push relativity to its extremes, where there are singularities either at the Big Bang or the black holes, doesn't seem to work the way we thought it would, or doesn't seem to work at all. Maybe it was really just an illusion that fails in quantum gravity. And basically, this is the preview of what's about to come. I want to present to you tentative cracks of cosmic causality. And these come from a combination of theoretical and observational arguments. So for black holes, this might be cracked or cracking in the future through observation of gravitational wave echoes that I'm going to introduce to you, or quantum hairs for black holes. So these are two different things that may have been observed already, or may be observed in the near future. In dark energy, tensions in measures of expansion or structures, so-called H0 and SA tensions, maybe cosmological cracks of cosmic causality. And at the level of Big Bang, the shape of the power spectra or biospectra of basic fluctuations that come out of Big Bang may point to cracking cosmocausality. But the idea is that these are observational probes that may very soon, or at least in the near short-term future, tell us about or test ideas that probe cosmic causality and potentially tell us that cosmic causality or just causality as a tenet of fundamental physics is not really correct, and it should be modified, either rethought or just thrown away if you want a fundamental theory of quantum spacetime. Okay, so that was my introduction. Hopefully that's excited or provoked enough so that you guys will stay awake for the rest of this. But again, please feel free to interrupt me at any point. So far things were being kind of general ideas or criticisms of the current paradigms. And now I'm going to tell you about new things that may lead to progress. So I'm going to start with the black holes, and this is basically one version of the black hole information paradox, which, as I told you, it's now its 50th anniversary. But the black hole information paradox has been actually gone through different waves. People have gotten excited and de-excited about it every decade or so. So the last wave was about 13 years ago by basically these gentlemen, Almeri, Marov, Polchinski, and Solly, who suggested this fireball paradox, which is kind of a slightly reformulated version of arguments by Samir Mathur, who is a co-organizer of this workshop in Stony Brook in the fall. And basically the argument suggests that so if you want to have Hawking evaporation and classical horizons, basically nothing special happens at the horizon, then you're in conflict with quantum mechanics. So these three things, quantum mechanics, Hawking evaporation, and classical horizon, cannot be correct at the same time. There is a solution, and the solution is basically instead of horizons, you have firewalls, basically places where information burn up. So the standard horizons, as you learn in your textbooks, cannot be correct. At least that's their proposal. And of course, there have been a lot of thousands of papers criticizing or studying, scrutinizing this. But this is a statement of a paradox that, depending on your mileage, you take basically different ways to approach it or solve it. But it is a paradox in a standard assumptions that we usually make to treat black holes and spacetime. Now, instead of kind of arguing ad infinitum about this, we could try to test what actually happens near the horizon. And that's the premise of gravitational wave echoes. So when two black holes spiral together and merge, they emit gravitational waves. We have famously detected these. That's the signal from the first event that LIGO saw, where mergers of two black holes. And the idea is that if instead of a horizon, as Einstein's general relativity predicts, you have a firewall or some kind of non-standard quantum structure near horizons, then after the merger happens, you may wait for a while, and then afterwards, you're going to see echoes, which probe this quantum structure of the black holes. And this time is not very long, but it's sufficiently long that can be seen basically shortly after the mergers, but separated from the merger event itself. So in terms of where this comes from, there are different pictures, geometrical or kind of non-geometrical pictures to understand this. But there is basically one way. This is kind of, in my view, this is the best way to understand why these echoes should be there. And that comes from basically understanding the basic quantum mechanics, that if you think about the black hole emitting Hawking radiation and you think black hole is a quantum object, the way that quantum objects radiate in vacuum, and that's Hawking radiation is radiation in vacuum. The way quantum objects radiate in vacuum is by going from excited state to a less excited state. And that's known as a spontaneous emission. That's, of course, something that Einstein first famously discussed, and now we have a very mature understanding of radiation in quantum mechanics. But if there is a spontaneous emission, as Einstein famously showed, there must be also a stimulated emission. That means that if you embed these quantum objects in a sea of radiation at the same frequency that the spontaneous emission happens, then that could stimulate the transition from excited to less excited state. And that's a stimulation basically is proportional to intensity of the incident radiation. So if you extend this analogy to black holes, that means that if you embed a black hole in a sea of radiation at the same frequency as Hawking radiation, then that incident radiation could excite or stimulate Hawking radiation. And that is what I call echoes. And in fact, if you follow the same calculations that Einstein did to derive a stimulated on spontaneous radiation, you could derive a reflectivity for black holes, which is given by the Boltzmann factor, e to the minus h bar omega over kt, where T is the temperature of the black hole, and in this case, it would be the Hawking temperature. So it suggests that if the frequencies of the radiation becomes comparable to the Hawking temperature, then horizons or black holes could have reflectivity of order 1, but for much larger frequencies, this reflectivity goes to 0, and then black holes are truly black. Okay. And it's an interesting observation that, in fact, when Einstein developed his theory of relativity, that was actually within a few months of when he developed the theory of quantum radiation for a spontaneous emission and a stimulated emission. And basically, the key equation for it is the one in green on the left. So these were both developed by Einstein around the same time, and it would be interesting that we might actually potentially see a combination of them. One is a quantum effect, the other is just effect of gravity in extreme. They can combine together and lead to gravitational wave echoes. So combination of these two basically leads to the prediction of gravitational wave echoes. And then you could have more concrete predictions for gravitational wave echoes. In fact, the potential for echoes was first pointed out a month after detection of gravitational waves in 2016. And there is a time scale for gravitational wave echoes, which is basically, if you imagine there is quantum structure near the horizon, the time it takes to go from the angular momentum barrier to this quantum structure is long, but it's only logarithmically long. So we know that if this structure approaches the horizon, the time goes to infinity. But if it's like a Planck away from horizon, this time is only logarithmically big. And this is basically a very concrete prediction that comes from essentially Kerr geometry, which is a prediction of general relativity, plus assertion of some quantum structure near the horizon. This LQG is the length scale for quantum gravity, which is basically a length scale, a proper length scale from the horizon at which quantum effects start to show up. And this idea of a stimulated Hawking radiation was first proposed by my former PhD student, Qingwen Wang, and postdoc Naritaka Ishita, who kind of worked out the amplitude of reflection. So you have basically these two things, that you have a time scale for these, for approaching this quantum structure, and you have an amplitude of reflectivity, and combination of these two give you a physical model for gravitational wave echoes. And on the right-hand side, you have a simple prediction or simple model for these gravitational wave echoes. And the takeaway from this is that you have the main events that's predicted by general relativity, but you have these subsequent echoes. And these subsequent echoes, the time for them is pretty robust because this log is basically the argument of log is very big. So if you change the length scale for quantum gravity by 4 orders of magnitude, the time scale for echoes only changes by a few %. So from 1 Planck length to say 10 to the 4 Planck length. The amplitude depends on kind of the model for reflectivity, and this stimulated Hawking radiation gives you a particular model for reflectivity, which is frequency dependent. To understand the time scale for echoes from basically a more robust kind of derivation, one way to think about the time is based on basically entropy of black holes. So basically, we learned from black hole thermodynamics, the work of Stephen Hawking, that black holes two basic thermal properties. They have temperature and they have entropy. And these two are kind of independent properties that you expect a quantum black hole to basically have. The temperature leads to Hawking radiation, but entropy is an accounting of the microscopic degrees of freedom of the black hole. But if you just take the standard picture of the black hole, you see there is a fundamental discrepancy. If you take a black hole and then look at the radiation in the spacetime of the black hole, in particular Hawking radiation, it turns out that the Hawking radiation that comes out of the horizon of the black hole, most of it doesn't go to infinity. Most of it gets reflected by the so-called angular momentum barrier, by basically classical gravity, which is basically what I showed here. And most of this Hawking radiation gets reflected back into the horizon. So if you wait long enough, you're going to actually feel the inner inside of this angular momentum barrier by Hawking radiation. And this is basically infinitely large if you write it in the proper units. So you could actually compute the entropy of this Hawking radiation, and it turns out to be infinite. So if you have a horizon at where basically where you predict the horizon to be, and it takes infinite time to get to it according to observer infinity, but at the same time, the entropy is infinite. Do I see? Sorry, oh yeah, so the entropy, so there's no echoes, but the entropy is infinite. But if you want this Hawking radiation, which most of it sits near the horizon is this down here. If you want it to have finite entropy, then you have to cut this off somewhere. So that means that takes a finite time to actually to get this cutoff, which I call quantum fuzz here. And that time scale is directly related to entropy of this Hawking radiation. And if you imagine this entropy is less than the Becker-Hawking entropy, which is the area of the horizon of the black holes, then actually gives you at least an upper limit, a lower limit in the time scale. No, sorry, an upper limit in the time scale for echoes, which is this log of entropy divided by 2 pi times Hawking temperature. So there is an L dependence here that depends on how high this angular momentum barrier is. But this is basically the time scale. And this is a very model independent. So I'm not basically assuming anything special about where quantum effects are happening. All I'm saying is that I'm assuming black holes have a finite entropy, and the entropy of Hawking radiation should be less than the entropy of the black hole. So that gives you where that time scale comes from. And notice this is not really a geometric argument. This is just an entropy argument. So we can go and look for these echoes. So I'm not going to, so this has been a long journey, it's 10 years old. There's been lots of ups and downs. Basically, the short answer to are there echoes in LIGO data? The answer is basically most LIGO events, there is no evidence for the echoes as I described for them. So this is the evidence, log of the evidence. So basically, it's somewhere between basically between 1/3 and 3. I see there is a question. Okay, sorry, I just saw this question. So for massless scalar field, the Hawking radiation is 80% in S-wave channel. Are you considering some specific quanta for Hawking radiation? So excellent question. You could consider all the quanta that you want. So I mean, generally people include the photons and gravitational waves because those are the only, or gravitons, those are the two massless particles we know that they exist, but there could be others. But basically, so those are the massless particles. Now you should include the massive particles for the total entropy if you're interested. They do not I mean, for big black holes, they exponentially suppress, so they don't really matter for this calculation as far as yeah, because the radiation is exponentially suppressed. But the point is that, in fact, this doesn't matter very much for this calculation. So this entropy, so the number of species that you have would go inside the log. So if you have, I don't know, if you have like 3 polarizations or 5 polarization or etc., they goes in, that kind of changes this log by a factor of order 1, and this is like, I don't know, 10 to the 80 here. So if you change the factor of order 1, put the factor of order 1, that doesn't really change this T echo very much. But this is a good question, and indeed one has to calculate. I mean, yeah, one should have to include it, and it does depend on the spin, but it all kind of the spin dependence, they all go into this kind of details of this log, and these are order 1 corrections that go inside the logarithm. So the final result doesn't change very much depending on a spin or yeah, depending on a spin of the particle or how many different species you have, basically. Very good. Other questions? Okay, hopefully that was clear enough. Okay. Now, the important thing is, oh yeah, I just wanted to say that, so basically most events, they're not, basically what this is showing you, the most events are not detected at high enough amplitude or high enough signal to noise that you expect to see the echoes from them. And indeed, basically the current observations or lack observation of the echoes don't really say much about their existence, just because the detection significance is very low. There is one exception, which is the biggest black hole merger that LIGO has seen, at least until last year. Right now, I'm not sure about the statistics, but I mean, the data is not public for the O4 yet. For this event, there seems to be around basically a log base factor of 10, of 1, which means a base factor of 10 evidence for these Boltzmann echoes, as I described to you for about stimulated Hawking radiation. And basically, if you look at it, these are basically these in the frequency time diagram or in the spectrogram. So this is the main event for this GW 190521. And there appear to be 2 echoes here. But of course, these are not very significant. There is also a lot of noise. You see there's noise here. These are all consistent with noise. So, so these 2 appear to be in the right place as are predicted for this event, but the significance is not terribly high. And so this is substantial evidence, but it's not definitive or strong evidence. Okay, so so that's the status right now. Basically, the data is not quite there to either rule out or rule in echoes. There have been other searches with basically more model agnostic models with or methods with many more parameters. And it's not surprising that they didn't really find evidence individually for echoes in any of the events that they look at. There are some exceptions. Basically, they're missing some events, and some of them they don't look for echoes. For example, say for 1 second echoes that we found here, this is 1 second after the event, and they only stopped, sorry. These searches basically went to 0.5 second. But basically, the short of this is that there is no kind of there's no strong evidence for echoes for any of the events, and there's only one that might have some evidence that's basically marginal. So I have another question here from Dipan. Are there cases where you get a superradiance amplification? So superradiance amplification, that's a good question. That's something that can happen if you have reflection of the angular momentum barrier for spinning black holes. It turns out that you also have, at least in the context of models that we have studied, but also most other models, if the reflection from black hole is not from these firewalls or whatever they are, if the reflection is not perfect, that could cancel the superradiance. So the only situation where superradiance could have a big effect is if you have basically almost perfect reflection from the firewall. But if there is imperfect reflection from the firewall, then there might be some superradiance, very marginal superradiance for the spins that we see. But at the end of the day, the absorption from the firewall is much more important. And so certainly for models that we looked at, there is no superradiance or averaging instability. There might be a bit of superradiance, but I mean, right now we haven't even observed the echoes. Now, if we could detect them, you could then look for effect of superradiance in it as well. But superradiance is an effect that's predicted, but it's not something that, at least currently, we could observe from, as I said, we haven't observed any echoes. If we do observe echoes, we could look for effect of superradiance in them as well. Okay, and so this is an updated list of different searches for echoes, which is up to 2023, basically. In fact, this last one is 2023. It should have updated this. And basically, there are some of them that suggest basic evidence at the level of a few percent. Some of them p-value is very small, but there are always caveats for many of these that I'm happy to discuss if you're interested. And there are also some that basically, there are also many searches that look for echoes but don't find them. But there are also caveats for why they may not find them. So basically, there are different ways of looking for echoes for different events. And some of them find something, but so many of them don't find anything. So there is no definitive conclusion from this. But why this is important is basically goes back to why we care about quantum mechanics as a theory. And the analogy here is basic analogy to look to searches for Higgs, which basically what drove particle physics or experimental particle physics for half a century. So the significance of Higgs to Large Hadron Collider, which was where it was finally discovered, is very much similar to significance of echoes to LIGO or other gravitational wave experiments. And that's basically if you assume unitarity, perturbative effective field theory, and the gauge symmetries of their theory. And for the case of particle physics, these are the gauge symmetries of a standard model. For gravity, it's the gauge symmetry of general relativity, which is the diffeomorphism invariance. It leads to idea of entropy or holographic entropy, the area law. So if you take all these three significant seriously, for on the right-hand side, it leads to the prediction of the Higgs. On the left-hand side, it leads to the prediction of echoes. And that's why we should look for them. Now, the same way that Higgs was not guaranteed, and in principle, they could have seen other things, the existence of echoes are not guaranteed either, but in some sense, it's the simplest way to resolve these apparent paradoxes that we have between these tenets of quantum gravity. Fortunately, the future is bright. The fact that we haven't detected definitively echoes, that doesn't mean that they won't be detectable. This is a prediction of how bright these Boltzmann echoes or stimulated Hawking radiation is going to be for future generation of the next generation of gravitational wave observation. So it's a bit hard to see this, but currently, so this the prediction from this model is that like the first event that LIGO saw is the one on the left. The prediction is basically less than one signal to noise. So you should kind of ignore this axis. Basically, we just look at the minimal model, which is the so-called TQ, which is the basically the temperature of the horizon is the Hawking temperature. So the signal to noise here, you see this is 7, this is 1, and this is less than 1. So basically the prediction is LIGO doesn't detect echoes. But at least for this first event, for the so-called 150914 event. So this is like basically too small, this echo. But Cosmic Explorer, which is the next generation of experiment based in the US, there is a similar one, Einstein telescope in Europe, that has been proposed. That's going to detect this as more than 10 sigma. So that's the key number to take away here. And that suggests that we definitely are going to either detect these echoes or rule them out based on based on these predictions. Another frontier is to actually simulate these echoes in numerical relativity simulations, which haven't been really done successfully. So this is something that my PhD student who just graduated has had been working on for the past few years, and these are kind of examples of the simulations that he actually has. He hasn't quite merged two black holes yet, but has simulations with numerical relativity with basically quantum boundaries that lead to echoes. And these are examples in a spherical symmetry where you see echoes, and you see that in fact in real numerical relativity, the time scale for echoes is not constant because space-time is dynamical. And this is basically the hot off the presses. These are simulations in a Kerr space-time where he kind of throws gravitational waves at a spinning black hole, and you see it reflecting off and coming back. And this is not quite mergers of two black holes, but this is full numerical relativity. And hopefully, in the near future, next few years, I can show you simulations of two black holes with these outer boundaries or membranes that could have echoes and mergers of black holes at the same time. Okay, so now I told you we can look for these in gravitational waves, but also we may be able to look for these in actually, let me ask a question. So how many more minutes do you think I should go?
Well, sorry. Can you? There
I
we
hear some echo.
Sorry, yeah, that was my fault. Well, we usually go for about an hour, because that's just when people usually have to go, but you're not bound by that. But that's the time when people might start to leave. But yeah.
Okay, so you think I should finish in like 10 minutes or
That'll be good. Yeah, possible, yeah.
Okay, 10 minutes. Okay. So right. So I think I'm going a little bit slower than expected, but let's just yeah. So thank you very much. So I just wanted to tell you, so basically the lesson from this, so I told you about how you could see this from gravitational waves. You may wonder, because we're now imaging black holes, should you expect something in the images of black holes? And so I'm not going to take you through the math of this, but basically the idea is that the same arguments that lead to echoes also suggest that there are quantum hairs that modify the Kerr metric, and these multipoles of the space-time would be different. So, so this is a work that hopefully coming out soon. I'm not sure. I've been promising this work is coming out for the past year, but hopefully really it's going to come out in the next couple of months. And the idea is that we expect these are basically multipoles, these Q1 and Q2, or some combination of multipoles, and they're going to be different from Kerr at a level of a few percent. So, and that's basically the same log of entropy that was there for echoes, we think there would be there for these multipoles. There would be log suppression. So these numbers are small, but not very small. Again, of order of a few percent. So that's I think that's another prediction. That's I think hopefully we can make this more kind of more robust soon. Okay, so I have like some kind of a list of exotic ideas. If you wonder what's okay inside the horizon, it's not really a black hole. What is it? So let me see in the view of time. I'm just gonna be a little bit more right. So a little bit more selective. So there is one idea that string theorists call fuzzballs. So this is something one can look for, and it has some of the right hallmarks for a quantum black hole. There are no event horizons. So that could be one thing. We don't know exactly what signatures of fuzzballs are, but it's certainly one thing popular with string theorists. One thing that we just, I think we submitted a couple of months ago, we call them as smart holes. And this is basically something between, so we're basically trying to make a kind of smarter analog for a black hole, but which has the right entropy and temperature. That's why it's called a smart hole. So it's basically a way of simulating a quantum black hole in a laboratory. Now, is it fundamental or not? I don't know, but we actually we have a model, and we showed that we can get both the temperature, right temperature, and entropy for this kind of smaller model for the black holes. And whether they have echoes or not, we're not quite there yet to answer that. But basically, the main thing is that we've managed to get the entropy of a black hole in a kind of matter system, at least on a computer right now. And another possibility that again we just published, I call them complex power balls, and these are based on a theory of quantum gravity known as the quadratic gravity. And this gives you the interesting thing is that the geometry is actually complex in the solutions that we find. But the interesting is that these are exact solutions, and in some sense, they kind of avoid the singularity in the complex plane. So they have, so basically you replace this standard picture of the black holes with something that's real geometry, and then in the middle there's the complex geometry, and then the other side is Euclidean. We don't really know what this physically means, but it's an interesting place that people haven't really looked, and it's based on a UV complete theory of gravity. Okay, so so the last 5 minutes, I just want to tell you that we could look for effects of these violations of causality in cosmology as well. So we could look in atomic clocks that are in a space, and so we have predictions for basically the kind of signals that you may see from a cosmological coupling of atomic clocks to a cosmological preferred frame. Because basically, if you violate causality, that means there is a preferred frame. Right now, the GPS data is here, but with the future GPS data in the solar system, or atomic clocks in the solar system, you can make this much more precise. And there are basically two targets depending on the kind of couplings. So I think the one interesting frontier are atomic clocks in a space, which could actually have fundamental tests of causality. Another interesting direction is tests of Lorentz symmetry in cosmology, but in particular, what a generic prediction of these models, in particular the so-called Tojava theory, is that G Newton and G Friedman are not the same. Friedman equation and Newton's law don't have the same coupling constant. And this actually may explain this offset between the measurements of Hubble in supernova and other experiments, the so-called H-naught tension. This is basically a model that's we worked on with cosmic Lorentz violation. And basically, the more cosmic Lorentz violation you could have, the closer is basically the Hubble constant that you would get from fitting cosmological data, and the one that's locally measured from supernova. So you kind of get closer. Now, again, this is not perfect, depending on the data set that you use, but with the right cosmological data sets, you could make these basically more consistent with local measurements of supernovae. And you could also solve what is the SA tension, which is another well-known tension in cosmology. The CGG is this model with the cosmic Lorentz violation, where you see these different measurements of SA become more consistent. So this is this cosmic Lorentz violation measured with different combination of data, but it's kind of interesting that from measurements of basically dark energy or cosmological expansion, you have this a different probe of violation of causality as we know it. And final thing I'm going to talk about is you may have this Lorentz violation at the Big Bang. In fact, there's some evidence that you have measurements of this Lorentz violation at the Big Bang nucleosynthesis and at the CMB scale, and if you just extrapolate it, it leads to order 1 violation of Lorentz symmetry at the Big Bang, which is what you expect from a quantum theory of gravity, like Tojava gravity. And that, in fact, could solve the horizon problem that I started the talk with. So basically, your sound horizon could be much bigger at the Big Bang than the standard model. And that could lead to some prediction for tensor modes for gravitational waves. And then also it could give you a specific predictions for the tilt of the power, the tilt of the power spectrum, which is this grain star, and the bias spectrum or a 3-point function. And these are all these are concrete predictions with a special, basically very smoking guns, like for example, a specific shape for non-Gaussianity that one can go and look for. So if you're interested about this, I have a popular book that's coming out called Battle of the Big Bang that talks about all of these models and more. And yeah, it's going to come out in May. So if you're interested in a good read, Carlo Rovelli calls an intellectual feast, feast away. And this is, yeah, so this is my conclusion. I'm just going to leave these basically here. But the main idea is that there are three places you can test causality in black holes. There are interesting things that there could be inside the black holes. You can test it in cosmology, and you could test it at the Big Bang. And that's the roadmap for discovery. That might be how the light gets in. Thank you.
Thank you very much. Yes, do we have any questions? So Roland's got his hand up, so you can go first, Roland.
Thank you very much. So if you see if you identify an echo or echoes with some characteristic time scale after a merger event, that means that you then can you then know something about some combination of this cutoff length scale and the angular momentum of the black hole. Is that how it works?
That's an excellent point. Yeah. So unfortunately, the information is about the cutoff scale is weak, but given that we have never observed this cutoff scale, then it's better than no information. So yes, but indeed, it would be some combination of a spin mass and this cutoff scale. If you want, I can go back to the formula which I had for you. I think it was the formula is here. Yeah, so the combination depends on the mass, a spin, and the nice thing is the mass and a spin can be measured in other ways, basically by fitting the GR waveform. And I mean, if you go and look up LIGO events, they all give you some mass and some spin with some error bars. But the echo, in particular, observation of echo tells you what this logarithmic can be, and basically what's inside the log is the entropy or a square root of the entropy of the black hole. So what you really are measuring is the entropy of the black hole.
Right. Okay. Thank you very much. Yeah.
You're welcome.
So that makes me think. I mean, maybe this is how it already works, but given that LIGO are able to constrain the mass of the black hole and the spin, does this, and then this, LQG is some universal parameter probably, this presumably permits some kind of stacked analysis where you combine and then you rescale appropriately for the mass of the black hole and the spin, and then you should see the stacked echo. Is this how it's already, because the tables you presented, they had like a p-value for individual ones, but presumably you can do it in a stacked way as well, right?
That's an excellent question, and in fact, that's really what you want to do. If you have many events, you don't want to look for echoes individually. You want to stack them. The reason that they don't do this is that they want to be model agnostic, and then they don't really know how the amplitude of echo in one event would be different or the same as amplitude of echo in another event. Does it scale with mass? Does it scale with something else? Maybe has something to do with the spin. And that's what you want to do. There haven't been that many stacked analyses. I've done basically this paper that I showed you. Let's see which one it was. This paper actually does try to do some stacking analysis, but the stacking is there. It's a bit tricky because I mean, if your predictions are off a little bit, and all the predictions are based on linear theory, for example, they're off a little bit, then stacking kind of does the opposite of what you wanted to do because they would be off a little bit. So then they're actually, instead of phases adding up, phases cancel. So it can be tricky, this stacking analysis, because the echo time delays are long and the signals are oscillatory.
Yeah.
So if there's a little bit of nonlinear effects, that would destroy any power that the stacking would have. So it's a tricky business. It's been attempted in this paper by Abed et al. It might be one or more other paper that try to stack things. There hasn't been any signal detection yet, but it could be because it's the nonlinear effects, or it could be because we don't really know how echoes in different events scale, how it depends on mass and spin, the amplitude exactly. But indeed, I agree with you, and in ideal world, we should be doing that, but it's kind of a tall task as things stand.
Yeah, also on this slide actually, I mean, if you take this left-hand plot seriously, the echoes are quite narrow in the frequency domain. Are you able to predict that frequency spectrum as well as the echo time?
Yes, and in fact, I didn't have too many technical slides on this, but in fact, the frequency of these is the horizon frequency, so it's actually proportional to the spin of the black holes, because basically this formula that I told you, this frequency is in fact the horizon rest frame frequency. So if you have a non-spinning black hole, the maximum reflection at 0 frequency. But for a spinning black holes, if you do this analysis properly, you just have to basically go to the rest from the horizon, and the black hole spins, the horizon is spinning. So this frequency is shifted from 0. So this peak is not at 0 anymore, but at basically horizon frequency. And that's actually the thing that's quite surprising, because I would consider that's where these white curves are. It's not. It's yeah. That has to do with the spin exactly. It's very predicted. So this actually the number is here. This is omega h, which is the horizon frequency divided by pi. That's so that's quite surprising. Now this may be a coincidence, but I mean this is why we got very excited about this, because you predict based on the spin of this object where the echoes should be seen, and that's basically around the horizon frequency. And we bang on see basically peaks, not one, but 2 echoes exactly where this is predicted. And that's the surprising thing.
And I guess I also have to ask, I mean, on the sort of the more boring side, are there potential astrophysical sources, like conventional astrophysical sources for echoes, like if you have accretion disks or something surrounding black holes, or other instrumental effects which could give rise to echoes, in the actual, in the mirrors of LIGO itself? Is this, presumably LIGO discussed this in the analyses, but do you have any thoughts about
that? Well, I think you should. Yeah, I mean, if you look for LIGO papers, they don't discuss this. They look for echoes in this event in one of their papers, but they stop at 0.5 seconds. So I think yeah. And then in other paper, they don't even include this event. So that's kind of what I was saying here. This paper stops at 0.5 seconds.
Yeah.
This paper just don't include this. I should say that this is a weird event because this is so massive that we don't really have, and the mass ratio is weird. So none of the models, even the GR signal, fits terribly well. So some are not. I'm kind of suspicious of this event being. I'm not quite sure it's very significant, but none of the GR models fit this very well. It could be that kind of the corners of the parameter space is not well explored by numerical relativity simulations here. So part of it could be that. I mean, for this event, I think noise is more of a problem than anything else. For black holes, the thing is there is nothing. I mean, all astrophysical disks are kind of tiny for around black holes because they're Eddington limited, and I mean their mass is very small. The black holes that you form from the collapse of neutron stars, like there is one event that we've seen like that, at least we're sure, the merger of 2 binary neutron stars. There could be other like neutron star black hole mergers that haven't been detected in optical. They may have a very massive disk because they're not, I mean, they're not really Eddington limited. And indeed, for those ones, that is a possibility. Now, the time scale is weird because, I mean, why you should see that this time scale? But yeah, it could be that if you have a neutron star here that merges with a black hole, and then at this point the whole thing collapses into a black hole. Or maybe if you have two neutron stars here, but I mean, for this event, it doesn't make sense because it's too massive. But for binary neutron stars, yeah, so the time delay may be the time delay from the merger to the formation of a black hole. And that's indeed for one of the events that we looked at, that is a possibility. But for this one, these are too massive to be neutron stars. So then you expect very little gas to be there, basically like 10 to the minus 7 or something of that order. So I don't think astrophysical astrophysical explanations are possible, but noise is always possible. And yeah, this is, as I said, this is not hugely significant. This is, at the end of the day, it's space factor of 10, which is substantial, but it's not really a detection as like particle physicists would like it.
All right, so last chance for questions. Please raise your hand if you do. If not, we can.
So let me just,
yeah.
I think, end by, let me thank everyone. Thank you for inviting me. This was fun. I wish I could be there in person, maybe another time. If you find anything interesting, don't hesitate to write to me. Just Google my name. And also, if you're interested in crazy things, you could buy my book, which is, I'm going to leave this. Sorry, I think this was as fast as I thought. You can buy the book, which has lots of interesting stories. And there are some things that I was not legally banned from saying. Okay.
Okay.